Welcome to Exercise 6 of our Environmental QGIS for Beginners course. By now you're probably tired of my voice, but hopefully the excitement of this next activity will make up for that. In this section, we'll be entering the exciting world of geoprocessing. This is where the magic happens. I'll be running you through how to add and use some simple and sophisticated tools in QGIS that will become an essential part of your analysis workflows. So to begin, let's open up the Exercise 6 workspace provided, which is located in your Training Data folder, 01 Training Data, 00 Workspaces. Save this to your working folders under 02 Training Outputs, 00 Workspaces as Exercise 6. There are various simple geoprocessing tools that are used frequently in a GIS. As most of our data today is in vector format, we'll be focusing on vector format tools. Just note that there are a whole range of raster-based geoprocessing tools and geoprocessing tools that can be used to swap between raster and vector formats. Generally speaking, geoprocessing requires a bit of planning to understand what the question is that you're trying to answer, and then defining a set of operations that will get you that result. As in life, there are many ways of getting from A to B, so it's a good idea to experiment with a range of tools, understand what they do, and also how to find out information about the library of tools out there. For this, QGIS Help is your best friend, and QGIS forums come a close second. It's important for any geoprocessing operations that the user is aware of what coordinate reference system each dataset is in. When processing data, issues can arise if the datasets being used are in conflicting CRSs. Typically, this will result in empty analysis outputs or error messages. QGIS can't always process data on the fly, so the best way to keep your processing clean is to reproject all your data in the same CRS. Note that you should always double check your outputs once they're processed to ensure the tool executed correctly. We need to ready our workspace for our processing, so we'll need to remove the on-the-fly transformations so only layers with the same CRS will overlay. In the menu bar, click Project, Project Properties. Under CRS, deactivate the Enable On-the-Fly CRS Transformation, OTF, and click OK. Then right-click on the Survey Boundary Final layer and click Zoom to Layer. This also refreshes the loaded layers. You'll now notice that your map canvas only shows a few datasets. This is because your workspace CRS is set at GDA 94/MGA Zone 50, so only data with that CRS will show in the map canvas. See eastern and northern coordinates shown in the info bar on the bottom and not latitude and longitude. Now we need to make sure that on-the-fly transformations are not automatically activated when we're geoprocessing. In the menu bar, click Settings, Options. Under CRS, choose the option Don't Enable On-the-Fly Reprojection and click OK. With this knowledge of required geoprocessing settings, we may find we need to reproject some of our analysis inputs. As an example, we may want to find out how much native vegetation is located in the survey boundaries layer we created in Exercise 6. So we'll need to reproject that layer to MGA Zone 50 to match the projection of the survey boundaries layer. In the table of contents, right-click Native Vegetation and click Save As. Then in the Save Vector Layer As field, complete the following. The format is Esri shapefile. We're going to save it as nativevmga50.shp under the folder 02 Training Outputs, 01 Shapefiles. For the CRS, select GDA 94/MGA Zone 50 from the drop-down or browse for it, and then activate Add Save File to Map. And click OK. You'll now see the survey boundary final data on the newly projected Native Veg MGA50 layer overlaid in the same location. Well done! You've just converted a geographical dataset in latitude and longitude in degrees to a projected dataset, or eastern and northerns in metres. With this done, you should be in a position to run a number of geoprocessing tools on those layers. The next step in our GIS analysis workflow is to clip the native vegetation dataset to the survey boundary extents. What this will do is exclude any vegetation areas that fall outside our boundaries, which we're not interested in for calculating area statistics. This geoprocessing tool will also cookie-cut vegetation that overlaps and create a new shapefile with the results. So click on Vector, Geoprocessing Tools. Clip. In the Clip window, select the following. The input layer is going to be Native Veg MGA 50. The clip layer will be Survey Boundary Final. For our output shapefile, let's name it Native Veg Extents and save it to the file 02 Training Outputs 01 Shapefiles. And then activate Open Output File after running Algorithm and click Run. Let's rename Clipped to Native Veg Extents. And remove Native Veg MGA 50 from your table of contents. Your map canvas should look similar to the screen. You should now see only native vegetation within your survey boundary extents. Note that if you find there's no data in the output shapefile, go back to your inputs and ensure they're projected to the same CRS. Another potential problem that will result in errors is that one of the input layers is corrupt or not topologically clean, as discussed in exercise 5. We can now dissolve all the native veg extents into one polygon. This makes for easier calculations of areas. We can dissolve based on an attribute field or dissolve everything into a single feature. So in the menu bar, click Vector, Geoprocessing Tools, Dissolve, and in the Dissolve window select the following. The input layer will be Native Veg Extents, and then activate the Dissolve All Do Not Use fields. The output shapefile will be Native Veg Dissolve, saved under 02 Training Outputs 01 Shapefiles. And activate Open Output File after running Algorithm. And click Run. Then rename Dissolved to Native Veg Dissolve. And remove the Native Veg Extents layer from your table of contents. Let's activate and drag the Native Veg Dissolve layer to the top of the table of contents. And then let's open its attribute table and review the contents. You'll notice that all the polygons are saved under one feature. This is called a multi-part polygon feature, as there's now one row of information shared by many polygons. It's important to note that the attributes in this table were based on the first feature in the original native vegetation layer, so they're not accurate for the new multi-part polygon. For this reason, it's good practice to delete all unwanted fields. In the Native Veg Dissolve attribute table, click on the toggle editing mode and click Delete Field. Then select all of the fields and click OK. All shapefile attributes should have a unique identifier, even if it's a multi-part polygon. So let's do this now. Click New Field and complete the following. The name is ID and the type will be a whole number, integer, with a length of 10. Then double-click in the new record and enter 1. Note that the geoprocessing steps you undertake and the order in which you perform them should be informed by the question you're trying to answer. In this case, the question was, what is the total area of native vegetation within all survey boundaries? A slightly different approach and order of tools would be used if the question were, what is the area of native vegetation within each survey area? We're now going to calculate the area of this one multi-part polygon. As we're using a projection, GDA/MGA Zone 50, our map units are in metres, so any calculation will also be in metres. When you think about it, this choice of CRS makes sense because you want to express area in metric units, such as square metres or square kilometres. It's then straightforward to recalculate areas in hectares or square miles if you prefer. In this exercise, we're going to be calculating the area in hectares. So in the Native Veg Dissolve attribute table, ensure you're still in editing mode, Then click the Open Field Calculator button and complete the following. Activate Create a New Field. The output field name is going to be area_hectares. We'll use HA as the abbreviation. And the output field type will be decimal number real of 10 and a precision of 4. Under the search functions, expand out the geometry listing. Then double-click the value area, which will bring up the value in your expression box. That is a $sign followed by the word area. This is going to calculate the area in square meters. We want to calculate our area in hectares, so we're going to need to divide this amount by 10,000. So complete the expression so it reads $area / 10,000. And then check if the expression is valid down the bottom here, and click OK. A new field will be added to the attribute table with the area in hectares. Click Save Edits. Then deactivate the Toggle Editing Mode button. Note that every time you open an attribute table, it opens as a new tab in your Windows taskbar, so make sure you close them if they're no longer in use. Time for a question. What is the total area of the native vegetation in your survey boundaries in hectares? Close the attribute table. For calculating areas in different measurements, you can use the following expressions. For square meters, just use the $sign area. Square kilometers would be $sign area divided by 1,000,000, and hectares is $sign area divided by 10,000, as we've just seen. We'd also like to look at the weed species that are located within these native vegetation areas. The question we could be trying to answer is something like, tell me which species appear in each survey area so I can create a tailored treatment plan for each one. Or in this case, we're going to be answering the question, how many weed species occur across all our survey boundaries? In the menu bar, click on Vector, Analysis Tools, Count Points in Polygon. Then when the Count Points in Polygon window appears, complete the following. The polygons we want to use are Native Veg Dissolve, and the points we want to use are weed points. The count field name will be weed count. And the output shapefile will be called nativevegweedcount.shp, saved under 02 Training Outputs, 01 Shapefiles. And then activate the Open Output File After Running Algorithm button, and click Run. Let's rename count to Native Veg Weed Count. And then activate and drag this layer to the top of the table of contents if it isn't already done so, and then open its attribute table and find the newly added field Weed Count. Check that this output is correct by having a look at the features. How many weeds are located within native vegetation? As a hint, the number will be located in the new field Weed Count. Close the attribute table, and then remove both the Native Veg Weed Count layer and the Native Veg Dissolve layers from your table of contents. So let's say we're interested in a particular weed species that's on a significant threats list and requires us to develop an action plan. For the sake of our analysis, let's focus on the variegated thistle. Part of our plan could be to define risk areas or areas that we want to monitor that are close to known weed occurrences. In this exercise, we want to create 500 metre buffers around our variegated thistle sites. The first step is to filter out our weed points, so we're left with only occurrences of that species to work with. So we're going to use a filter expression to achieve this. In the table of contents, right-click Weed Points and click Filter, then double-click on Common Name in the Fields window, click Equals under Operators, click All under the Values window to bring up unique values for that field, Double-click Variegated Thistle, and then in the Query Builder window, check that your expression looks correct on the screen. So it should be common name in double quotes equals variegated thistle in single quotes. And click OK. Only the thistle points should be visible in your map canvas now. So how many thistle points are there in the map? Review the weed points attributes table to get this answer. Now we need to create the 500 metre buffers around the remaining points. In the menu bar, click on Vector, Geoprocessing Tools, Fixed Distance Buffer, and complete the following. The input layer is going to be weed points. The distance will be 500. Again, this is based on the CRS, so it's indicating metres. And the output shapefile is going to be called Buffer Thistle 500 metres. And save it to 02 Training Outputs 01 shapefiles. And activate the Open Output file after running Algorithm button. And click Run. Activate and drag the layer so that it's under the weed points layer in the table of contents. Then zoom in closer to one of the weed locations. Now let's use the measuring tool to ensure the buffer is a total 1000 metres wide or a 500 metre radius. And let's rename this layer to Buffer 500 metres. Note that the buffer tool is useful on line and polygon geometry as well, and can be a powerful way of assessing the proximity of features, creating exclusion zones and sensitive areas, and many other applications. So let's say you've now been emailed some additional weed location coordinates to add to the weed points layer. As there are only 2 locations, it's going to be quicker to add them within the workspace rather than setting up another join from a spreadsheet like we did in exercise 5. So to enable us to enter specific coordinates directly to the map canvas, we'll need to install a QGIS plugin. Remember that plugins are useful additions to the core QGIS product developed by the open source development community. Some plugins are more useful and universal than others, owing to the fact that some are developed with a very specific use in mind. For this exercise, we're going to add a plugin that's going to allow us to quickly enter coordinates and turn them into point features. So click on the Plugins menu and open Manage and Install Plugins. Then search for Numerical Digitize. This might actually already be installed. If not, click on Install Plugin, then close the Plugin Manager. Now right-click on the weed points layer and click Zoom to Layer. You'll see that we still have a filter on the layer, so we're going to turn this off before continuing. And to do that, right-click on weed points and click Filter, then click Clear to completely remove the expression, and click OK. You'll notice all weed points are now displaying. Click on any other layer, then back onto the weed points layer to reactivate it. Now click on Toggle Editing Mode. Click on the newly installed plugin Numerical Digitize. This should be located next to the editing tools in the top toolbar, but if it's not showing, you might have to restart QGIS. But first, remember to save your work. Then in the pop-up table, add the following locations. X1 coordinate is going to be 682,374, and the Y1 coordinate 619,4730. The X2 coordinate will be 683,752 and the Y2 coordinate 619,2893. And then click in the CRS of the layer and click OK. Give it an ID of 30 and 31 in the pop-ups attribute table consecutively. These weed points will now be added to the map canvas within the survey boundary Site C. Notice that they're coloured blue as they're now null values in the attribute table. So if you want to see why that is, review the symbology for the layer. Open the attribute table for weed points. These 2 weed locations are also added as new blank records within the attribute table. Double-click on the cells and add the following values, which I'll put up on the screen now. If it's easier, you can copy and paste from one cell to another using Ctrl+C and Ctrl+V. Remember, for many new records, you could either do a join or use the field calculator. When you finish, click off Toggle Editing and click Save. The new point locations and associated attributes are now permanently saved to the weed points shapefile located in your 02 Training Outputs 01 Shapefiles folder. Close the attribute table. Save your workspace and exit out of QGIS. So that brings us to the end of exercise 6. We've given you a taste of how geoprocessing works with some select examples, and I hope that this has ignited a passion in you to go and discover what other tools and plugins there are at your disposal in QGIS. And remember to start with the question you're hoping to answer and break it down into steps and build a plan of attack from there. Good luck with it all.